You said
You got one line.
You said you were thinking about changing when the asset will start. Is that happening or is it yet?
I already changed it.
Yeah.
Oh, I see, yeah. I'm like, I only sent one email, but yeah, when I changed the dates again, gotcha. Sorry about that. Those are
I need to figure out how to disable those emails because currently I've got it set up so I can like anytime an assignment is created and modified or yes. Wait, no. Actually, sorry about that.
So, Unit 2 is all about rotation, well, mostly about rotational motion. There's a few other things in there too. But, let me ask you this. Let's say I got a pizza, and the pizza is rotating counterclockwise, and there's a pepperoni right there. What kinds of quantities can we use to describe the motion of the pepperoni? This is a famous, Confucius question. How do we describe it? Angular velocity, yeah, like
Angular kinematics.
we got tangential velocity. We got angular acceleration, regular acceleration, displacement, and sorry, wrong spot. Theta. Yes, there we go. What's the connection between all these equations, all these variables? How do I go back and forth? Yeah. Okay. So S equals R theta, V equals R omega, and A equals R alpha. And that's all well and good, I mean, that's math. But conceptually speaking, what do these quantities mean? What does theta mean? It's how far you've rotated. It's measured in radians, which again are not a real unit, and it's a ratio between two of the same units. But this can tell us how far the pepperoni has rotated through some angle. Okay, that's fine. What is angular velocity? Why is it different than regular
You
velocity?
record the whole class?
What's the connection? What's
You
the
send that
difference?
to me? Yeah, for sure.
Okay. If I wanted to draw this pepperoni is going around in a circle. If I wanted to draw the velocity of the pepperoni, how would we do that? Okay. Which way is it pointing? It's tangent. The velocity of things going in a circle is always tangential to the curve, tangential to the circle. Okay. So this is V. Let me ask you this. Is the pepperoni accelerating? Assume that its speed is constant. It's spinning and the speed is not changing. Is it accelerating?
Yes.
Why?
This is changing
Because the
direction.
direction is changing. As it goes around in a circle, the direction of this velocity keeps changing, so it's accelerating. Okay? If I wanted to draw the acceleration of the pepperoni, which direction is it?
It's perpendicular.
It's always going to be toward the center. Okay? So if something's going in a circle, the velocity is tangential to the circle. The acceleration points from the center. They are perpendicular, which means the work done by whatever force is making it go in a circle is. Okay. No work is done by centrifugal force because there's a right angle. Okay? How do I draw omega? How do I draw the angular velocity? Right hand. If it's spinning this way, the angular velocity points out of the board. If it's spinning this way, the angular velocity points into the board. How do I draw alpha? Depends on if the pizza is getting faster or slower. If it's faster, faster. So if it's speeding up, alpha would be this way. If it's slowing down, alpha would be that way.
Is alpha always off the face, for lack of a better term, of what you're doing? It's oriented to that direction?
Yeah. Actually, all of the angular variables are going to be perpendicular to the plane of the rotation. Like if it rotates from here to here, theta points this way.
Right, but I mean just in angular acceleration specifically, is it always off the face or does it ever, I mean, if it's negative it goes off the back, but as long as you're positive, it always points off the face, right? So right hand rule still applies.
Yeah, right hand rule always applies to these. Yep.
What's angular acceleration if the angular velocity is constant? 0.
Okay. What else? Is there a force on the pepperoni? There has to be, or it wouldn't be going in a circle. Which way does the force point? Towards the center. Okay. We have a name for forces that make things go in circles. The centripetal force, it's mv squared over r. You don't need to remember the equation, but you should know it points toward the center of the circle. You should also know that the net force on anything going in a circle is always this. It doesn't matter if it's a yo-yo or a satellite or a pepperoni. If something is going in a circle, the net force has to be that. So the net force on a satellite is not 0, it's actually that. The satellite is going to be falling to the ground. There's nothing stopping it from falling. Other than the fact that when it hits the ground isn't there. That's why it doesn't collide with anything, because it's got this whole side of it. But yeah, there is a net force, and it's not 0, it's pointing to the center. So acceleration, net force, velocity, angular velocity. Okay. Those are all of the ways that we describe things that are rotating. Let's talk about torque for a second. Torque makes things rotate. Okay. This is Newton's second law in angular form. Forces make things accelerate, torques make things accelerate angularly. Okay. So torque, sorry, I got my glass of color. Torque is RF sine theta. Again, you don't need to memorize the equation, but you should know what these things mean. I'm going to do something that never turns out well. I'm going to draw a wrench.
Oh,
So brace It helps if I put a little more detail.
Draw the X nut first.
I gotta draw the X nut first. This is what I've learned. That helps to guide the rest of the process. So that's my wrench. If I want to increase the torque on the nut, this thing, well, the bolt is that's technically the. If I want to make this thing rotate more, if I want to increase the torque, what can I do? What are my options?
Increase your radius.
I can do that. What the heck is that?
Isn't that going force from the center?
Yeah, but no. Yeah. Here's the idea. Let's say there's some force. Okay? I'm pushing on the wrench there, for example. Okay? If this is my force vector, R is the vector that goes from the axis of rotation, so from this point here, to wherever the force is being applied. So from the axis to the place where you're pushing. Okay? So if I increase R, I increase the torque. In other words, pushing here is easier than pushing here. Opening a door at the edge is easier than trying to push by the hinges. Okay? That's why doorknobs are always on the edge of the door, because it's easier to push there. So this force creates more torque than that force does, because of this. That's what you should understand about this. Okay? I can also push harder. I can make my push bigger, that's kind of obvious. And then how do I maximize this thing? Yeah, 90 degrees. In other words, pushing like that is going to be more effective than pushing like that. Yeah. What happens if I do this? How much torque am I creating? None, which makes sense because that thing's not going to rotate if I'm doing this. Okay. So this will create torque, but it's not very effective. And then this is going to maximize.
In the wrong
Sure. it'll, yeah, what would that be? Loosen? Yeah, that'll loosen it more, but it'll still create torque. All right, pretty good. Okay. Let's look at this equation for a second. We know what alpha is. What the heck is I? How would you explain I to a 5-year-old? Yeah, it's the moment of inertia. It's that moment when inertia makes sense. It never comes, but it is.
How difficult it is to get something rotated.
Yeah. How difficult it is to rotate something. And we did a bunch of math, a bunch of calculus, I'm not going to do that. But you should should understand that as you move mass away from the axis, it becomes harder to rotate. If I've got an axis and I've got just a little, blob of mass, and it's a point mass, the moment of inertia is just mr squared. If I have more than one mass, I have to add them all together. But this is the basic idea. You take the mass and multiply by the distance squared. So as the mass gets further from the axis, it gets exponentially more difficult to rotate. So I did a demo one day in class where I had a hockey puck, and I had like a hoop, and they had the same mass and they were the same size. Which one's easier to rotate? Yeah, this one. Because there's more mass that's closer to the axis. This one, all the mass is pretty far from the axis. So as m gets closer to your rotation axis, it becomes easier to rotate that thing. So if you roll both these down a hill, this one would roll more easily than this one would. If I gave you two objects, like, I don't know, like a box and something that, looked like that, and they had the same mass, you should know that this one's easier to rotate than that one is. What else? We can define something called angular momentum for my pizza, and it's going to be conserved. Oh, real quick, if I have two pepperonis on here, this one and this one, which one has a higher angular velocity?
Angular velocity?
They're the same. Trick question. This one has a higher tangential velocity, but they have the same angular velocity, assuming that they're both stuck to the pizza. They're both doing circles at the same time. I also have angular momentum, okay, which is the moment of inertia times omega. It points in the same direction as omega, so if the pizza is spinning this way, angular momentum points that way. It is conserved. We saw a couple of examples of that, like for we had the figure skater. It was like doing one of these, right? And then she did one of these, and then she went faster. Why does that happen? What's going on? L is a conserved quantity. So at the beginning, when her legs are out, there's a really big moment of inertia, because her mass is further from the axis. And then she's not spinning very fast. And this is, some L, something new. And this number needs to stay the same because it's a conserved quantity. When she brings her arms in, her moment of inertia gets smaller because the mass is closer to the axis of rotation. And that means omega has to get bigger. That's the most, there's a bunch of different examples, but this is kind of the more common way we describe the conservation of angular momentum. Any questions on that? We talked about static problems. We had this problem where there was like a board and some ropes, anchor staff or anybody. What two assumptions did you guys make on that problem? You said that the acceleration is zero. In other words, the velocity of the board is not changing. There's one more assumption here.
Force of gravity is the same in the law.
I guess there's a couple.
Or uniform density.
Well, that's true. Okay, there's like 9 assumptions, but the ones that are important are these two. And there's a distinction here. If the net force is 0, the velocity is constant, and the acceleration is 0. If the net torque is 0, what do we know about power? Which means that the angular velocity does not change. Is it possible for something to be rotating and for the net torque to be 0? Yes. As long as the velocity is not changing. So I could go out into space and take this stapler and spin it, and it would stay here and keep spinning. But as long as it's not getting faster or slower, the net torque can still be 0. So it's not that it can't be rotating, it's just that it can't be accelerating. Now in this case, it's not rotating, so it needs to continue not rotating. The angular velocity is 0 and it's staying 0. But the net torque being 0 means that the rate at which it's rotating cannot change. It's basically just the angular version of this exact thing we did in like chapter 2. So if all the forces balance, the regular velocity can't change. If all the torques balance, the angular velocity when this thing snapped, we basically have like a trap door with a hinge right here, and this thing is swinging this way. I've got a whole bunch of little gravity vectors acting on atoms. I can pretend that all of those vectors are only happening in one place. And it's called the center of mass. So you can pretend that gravity is only acting in one spot. The center of mass is nice because you can always pretend that all of the masses in a rigid object are only located in one point, which is the center of mass. That can be really useful. Now, if the object is uniform, that point is in the actual center of the object. But it doesn't have to be, because I can have a situation where I have like a non-uniform board, so it's like heavier on one side than the other. So the center of mass might be like right there. If that's the case, I put my finger right there, it's going to balance it. Uniform means the density is constant everywhere. That's this situation. Center of mass. If I have like a Pringles can or something and I'm trying to tip it over, at what point does it tip? How do I know? When the center of mass passes over the support point. Remember that video we watched? The plumb bob guy, right? I'm not gonna make you do integrals.
That's kind of you.
When they go to that stuff,
When the center of mass, yeah, passes the support point, that's when it tips.
Is that what that point is called? Is a support point? Or are you just making that up?
I don't think it has an actual name.
Could just be like
The point where it's touching the table. So, let's see. Plumb bobs, center of mass, this stuff. We have the bulk modulus that tells you how much something compresses when you apply pressure on it. Young's modulus tells you how much something stretches when you apply force on it. That's pretty much it for chapters like 8 through 11. I'll go through the test in a second here, see if I missed it.
So for the bulk modulus, the higher the number, the more it compressed, easier it is to compress, or
The harder.
the harder it is to compress? And then young, the higher the number, same thing.
Higher number means more difficult to stretch. Okay. Let's talk about fluids. Fluids are liquids and gases. Liquids are typically incompressible, so the density stays the same. Gases are typically compressible, so the density does not stay the same. If I were to climb Mount Everest, what happens to the air as I get higher? Yeah, it gets less dense. The pressure decreases and the density decreases. If I were to plot that as a function of my height, what would it look like? Yeah, it's not linear. It's going to be a curvy exponential type thing, because as you go up higher, the air is less dense, and so the pressure changes non-linearly. What if I go to the bottom of the ocean? What happens to the water? The pressure increases. Sorry, I'm plotting pressure, I should. I'm plotting pressure, not density, sorry. Although it looks like a rho, it's not, it's a P.
P?
Pressure. Okay. If this is water, then this is linear. Because even though the pressure increases as you go down, the density does not change. That's because liquids are typically not compressible. Not very nice. Approximately not compressible.
What does it represent?
Just depth, distance. Sorry, I should label my axes.
Yeah.
I should, yeah. Basically, you climb Mount Everest, as you get higher and I should flip. When you climb Mount Everest, as you get higher, the pressure decreases and the density decreases. When you go in the ocean, as you go down, the pressure increases and the density stays the same. And the air is not linear and the water is.
There's exponential.
We got Bernoulli's equation. It's a whale. Now it's an S It's an airplane. The air on the top is going faster than the air on the bottom. There's pressure down here. What happens to the pressure on top? It's nil. Bernoulli's principle says that pressure in a fluid decreases as the velocity increases. So fast-moving air, little pressure. Slow-moving air, bigger pressure. That's how airplanes fly. We have Bernoulli's equation, but it'll be underflung the sheet. It just says basically that the pressure is affected by height. So you go up or down, you get changes in pressure. And then by velocity, as the speed of the flow changes, you get differences in pressure. Those are the two things that can affect the pressure. Let's say I got a pipe and it's fat and then it's skinny. That's a significant difference right there. Get in there, you. If this is an incompressible fluid, something stays constant as I move from here to here. Flow rate. Very good. What is the flow rate equal to? Yeah, it's the area times the volume. And that's conserved. That has to stay the same. Even if it is compressible, as long as it's a steady state, it's still going to be conserved. So constant flow rate. That means that if I've got a certain velocity here, and the area is big, and then the area gets little, what happens to the velocity? It increases. So the fluid has to go faster through the skinny pipe than through the big one. What happens to the pressure? Yeah, the pressure goes down. Because again, faster moving fluid gives lower pressure. What does Pascal's law say? So Pascal's law says that in a fluid, forces propagate isotropically, essentially. In other words, if I go to the bottom of the ocean and I hide in a cave, it will not shield me from the pressure. Just because I have a roof over my head, that's not going to protect me from the pressure. Because the forces are going sideways and up and down in every direction.
Do we be able to identify like Boyle's law, Pascal's law?
No, not Boyle's law. We'll talk about Boyle's law in a minute. It's just not that much because we're not kidding.
Will you repeat Pascal's law for me?
The forces in a fluid propagate equally in all directions. Like if I go to the bottom of the ocean, the force on my arm and my leg, and it's all the same. The force is up and down and sideways and diagonal. It's all the same force at a certain depth.
So it doesn't matter if you're contained or not.
Yeah. So if I go inside of a cave, and I'm like, oh, well, there's a roof above me, so that I can't shield myself. I can't open an umbrella and protect myself from the pressure.
Okay.
Because the pressure is, maybe that seems obvious to you guys, the pressure is caused by the weight of the fluid above your head. So if you open an umbrella, even though you're technically shielding yourself from the column above your head, it doesn't matter because that's pushing down on the fluid next to you, and that's pushing sideways and up and down. You can't escape force. There should really be a more elegant way. I always struggle to explain that one. So Pascal's law, Bernoulli's law, we have Archimedes' principle, which says, what is it? Cannot run from pressure. Archimedes' principle basically says that if you weigh 10 pounds and you want to float, you have to displace 10 pounds of water. That's why if you have a beach ball and it weighs I don't know, a pound, maybe, you don't have to displace a little bit of water. If it weighs 1 pound, it's got to displace 1 pound of water. Okay. So if something weighs more, it has to displace more water. Basically, the buoyant force, the force pushing up, is equal to the weight of the water you're displacing. At a certain point, what's that? If it floats. Well, even if it doesn't float, because what happens here is if I've got like a rock, and the rock weighs, say, 100 pounds, we'll do newtons, 100 newtons. It needs to displace 100 newtons of water. The problem is 100 newtons of water is going to be bigger than the rock. So it's not capable of displacing 100 newtons of water. This is what happens when something is denser than water. This thing is less dense than water. This thing is more dense than water. This thing doesn't need its whole volume to displace, its weight. This thing can't displace. Then you have sea turtles that are jerks and they're just like usually buoyant. You can do whatever they want, go scuba diving on it.
If it's just as dense as water, just kind of.
It just sits there, doesn't move now. You ever seen a balloon after like 3 days?
Top or?
It's wherever it was when it's, something bumps. It's like when you have a helium balloon in your house and after like a week, it's just kind of sitting there in the middle of the front room, ominous. Like it's not going, it's like this high off the ground, it's not going up or down. That's neutral buoyancy. And if you push it, it's like, it just stays there. You like draw a clown face on. Here's one. If I'm in a canoe and I've got a rock in my canoe and the rock weighs 100 pounds and I chuck it into the lake, does the water go up or down? Down. Why? Because of the science.
It makes a lot more sense if you say your rock has like a bajillion pounds, it weighs like a bajillion pounds, but it's small. So it's like made of like, it's as dense as like neutron star stuff or something.
Think of it this way. When the rock is in the boat, if it weighs 100 pounds, it's just wasting 100 pounds of water because it's floating. 100 pounds of water may be this big, right? 100 pounds of rock is only like this big. So when it's in the boat, it's displacing this much water. It's displacing its weight. If it weighs 100 pounds and it's floating in the boat, it's displacing 100 pounds of water. But when you chuck it in the lake, it's only displacing its volume. Because if it's this big, it's pushing that much water out of the lake. And so in the boat, it's displacing this much. In the water, it's only displacing this much. So it displaces more water when it's floating than when it's not floating. So the water level actually goes down. Any questions on that?
Actually, I've got one. Does the surface area or volume of an object have any effect on how much water is displaced, or what's the relationship there?
Nope, just the mass.
Just the mass?
Yeah. It might change how it orients itself as it, as it flows. So
Density is lighter than water.
Sure. Density is mass over volume. And so really, I mean, all that matters is how much the thing weighs. If it's more dense than water, it'll sink. If it's less dense than water, it'll float. And the amount of it that gets, submerged. Basically, this has to be the same weight. This much water has to be the same weight as the object.
The amount that is displaced has to be the same.
The weight of the water that you're displacing has to be the same as the weight of the object, if it's floating. Right? Because what happens here is, you've got the force of gravity pulling down, and you have a buoyant force, which is equal, it's still equal to the weight of the water you're displacing. The problem is, the weight of the water you're displacing is not as big as the weight of the object, because you're not displacing enough to counteract. Okay, gravity is a force. Moving on. It's a really weak force. Everything feels the gravity, like my face and the whiteboard. It's an inverse square law, because it has a square on the bottom. And basically, if you double the distance, you get 1/4 as much force. If you triple the distance, you get 1/9 as much force. That's important for not dying and getting sucked into the sun. It's also important when you're doing like waves. sound might, you get further away and you get less intensity, because the energy has to travel over a larger sphere. That's why speakers aren't as loud from far away. We never talked about decibel in this class.
We did not.
I just realized, yeah,
Is that actually on the test?
I don't think it is. I just realized I knew it. It's not that complicated. Maybe we'll spend 5 minutes on Tuesday just for kicks. It's not that hard, it's just a scale we use to measure how loud something is. But it's log-based 10, it's kind of cool, because they don't sing. Let's say I got, actually let's do this. Let's say I got like a planet, and I got a satellite. What do Kepler's laws say? Yeah. Kepler's first law says that things go in ellipses, where the thing you're orbiting around is at one of the foci, and then there's nothing at the other focus. That's Kepler's first law. Kepler's second law says that if this thing's tracing out triangles, all of these triangles have the same area, which basically all that means is that when you get closer to the sun, you go faster. So this is coming around, doing this thing going kind of slow, and then it's like, you get faster as you get closer to the thing you're orbiting. Kepler's third law is an equation you don't have to memorize, but what you should know is that t squared is proportional to a cubed. A is the semi-major axis. So basically, the further you get from the sun, the longer it takes you to go around its orbit. So you would expect Pluto to have a longer orbit than Mercury.
So P squared equals that?
What's proportional? There's like what, GM over 4 pi, or there's some other mechanical constants for that. You don't have to memorize the equation, but you should know that as the semi-major axis increases, the period also increases, not linearly. We can have a satellite going around in a circle. We already kind of talked about this. It has a tangential velocity that points that way, acceleration points that way, and force points that way. Escape velocity. Yeah, it's a thing. I'm trying to think what I asked. I'll look at the test and then make sure I'm just trying to go through. Just because you don't have to do math, it's mostly concepts. Circle. You guys know what the period means?
How long it takes to do one?
Yeah, the period is the amount of time it takes to do one complete cycle. The frequency is the number of cycles you do per second. They're inverses. Let's talk about spring. F equals kx, that's Hooke's law. As you stretch a spring, it gets harder to stretch it. This is linear, so if you double the stretching, you get twice the force. So the energy stored in the spring is non-linear. You double the stretching, you get 4 times the energy. Every spring has a nice happy place where all the forces are balanced. That's called the equilibrium. If you stretch a spring down to here, it will oscillate back and forth. Between here and here, the distance between the equilibrium and the midpoint of the max is called the amplitude. The amplitude does not affect the frequency of the oscillation. We saw that with Miley Cyrus and Penny. If I wanted this thing to oscillate faster, what could I do?
Increase the spring constant or shorten it?
Yeah, I could use a stiffer spring. Stiffer springs oscillate faster. That's why the speed of sound is higher in metal than it is in air. I could also use a smaller mass. That would increase the frequency. If I plot this thing,
Is it kx or negative kx, sorry?
Oh, yeah, it's negative kx. And that's because the force and the displacement are always opposites. So if you take a spring and you squish it this way, the force points that way. And if you pull it this way, the force points that way. Basically, the force always points towards equilibrium. That's a restored force. When you squish it, it doesn't want to be squished, so it pushes back the other direction. That's why it's negative, because F and X are always opposites. Springs. You should know, when this thing's oscillating back and forth, where the velocity is a maximum, where the velocity is 0. You should know where the force is at a maximum, where the force is 0. You should know where the kinetic energy is at a maximum, where the kinetic energy is 0. You should know where the potential energy is at a maximum, where the potential energy is 0. Where the acceleration is at a maximum, where the acceleration is at 0. Did I do that too fast?
You ready?
Yeah. Down here at equilibrium,
Wait, that was mine.
or, sorry.
Is that the same?
Wow. Here at the amplitude, the force is at a max. Let me do this. Max. And that, potential energy is at a maximum. Displacement's at a maximum. Force is at a maximum, and acceleration is at a maximum. That's
What's the U?
the potential energy, the elastic potential energy in the spring.
The force and acceleration.
And that would be at both ends, bottom and top.
Right. Yeah, that would be here and. And then the velocity is 0, and the kinetic energy is 0. Here, the velocity is at a maximum, the kinetic energy is at a maximum. The potential energy is 0, the displacement is 0, the force is 0, the acceleration is 0. If we have coupled oscillators that are connected together, we can make waves. The distance spanned by one cycle, this is a cycle. This is also a cycle. So this distance for equivalently this distance, that's a wavelength. The velocity of a wave is equal to the wavelength times the frequency. Frequency is the number of bumps you count as the wave goes by. So if I put a detector here, bumps per second basically would be your frequency. The velocity of waves in a string depends on the tension. As it gets more intense, the velocity goes up. It also goes up when the string gets lighter. We have mechanical waves that require a medium to travel through. Light is not a mechanical wave, but like a wave on a slinky would be a mechanical wave. Sound is a mechanical wave. Sound is a longitudinal wave. This is a transverse wave. In a transverse wave, the oscillation is perpendicular to the propagation. Anytime you have a mechanical wave, the medium itself is not traveling. It's staying in one place and it's just oscillating back and forth. So in this situation, the molecules or whatever they are just wiggling up and down. But the wave's going that way. So that's a transverse wave, because those are perpendicular. If you have oscillation, like in a sound wave, you have oscillation like this, propagation in the same direction. That's a longitudinal wave. We also have traveling waves that look like this. That's the amplitude. K is the wave number. Omega is the angular frequency. This essentially controls how fast the wave is traveling. This controls how many bumps you have basically within a certain distance. We have resonance, which is where if you drive an oscillator to the natural frequency, then its amplitude increases, that's resonance. We had beat frequency, which was the difference in two different frequencies that makes that beat sound. We had the Doppler effect. If you have an object traveling towards you, then you should hear a higher frequency, it will be blue shifted. If it's traveling away from you, it will be a lower frequency, it will be red shifted. And it's a lot of freaking physics. It's like 6 weeks. I'm like racking my brain like, I think that's all we talked about. Let me check the test. Why is there a mirror behind me? What?
The projector's not on.
I did. I've done this a few times.
Just a few.
I've often wondered, like, if I just sat down in a room with a blackboard marker and so it's like, tell me everything you know about physics, like, how long that would take? Days.
I think it depends on what speed you were going.
Yes, not physics.
You should know what a node and an antinode is. You should be able to identify them and draw pictures of standing waves and pipes and on springs. You should know that endpoints don't count as nodes or antinodes. You should be able to figure out how many wavelengths are inside of a pipe, a standing wave inside of it. You should know what one complete cycle looks like. Like if I go from here to here, that's one complete cycle. Or if I go from here, that's, you should know what one full cycle looks like of an oscillator. You should know what period and frequency mean. And their units. You know that sound is a longitudinal wave. It travels faster. It's different materials. And that's pretty much it. It's a lot of stuff. It all fits in. Resonance is when you drive an oscillator at its natural frequency and the amplitude increases. I think thank you. You should know what density means. When something is more or less dense than water, you should know what that means in terms of how much it's dispersed. Like if I tell you that something is more dense than water, you should know that. And I tell you that it has, if I tell you that something is this big, and it's more dense than water, you should be able to, you should understand how its mass compares to water that's of a similar size. Like, if something is more dense, that means a certain volume has more mass. Like if a rock is more dense than water, that means that the same volume of rock has more mass than that equivalent volume of water. Like 100 pounds of bricks is smaller than 100 pounds of feathers. Like, how do I explain this? Yeah, 100 pounds of bricks, 100 pounds of feathers, right? That's, you should conceptually understand what that means in terms of I don't wanna give away too much. I think that's pretty much everything. You guys have any questions?
What is the nature of that tourism?
I moved the homework back, and the take-home test is due Tuesday, is that